Hi there, and welcome back to Triplicate, and today we're back on the main green synthesizer, and yes, the front panel is all wired up and ready to go, but we're not going to do anything with this today. We are going to get the audio interface working. And to do that, we are just going to attach it straight onto the board, like that, in that corner. So I'm going to do that. I'm going to mount that there, and then we'll start looking into how we wire it up, and then we'll start looking into how we drive it. Okay, so that little audio output board has on it a UDA1334 chip, and this is the datasheet for it. If you really want to get into it, you can download the datasheet yourself. Important things to note is it uses the I2S bus, which is the standard audio digital interface. It'll generate its own sample rate using a PLL, so you don't have to provide it with a master clock, which is good. It has various options which are brought out to connections on the board from the pins on the chip. The clock is in audio mode, we've set that. Okay, our sample rate is 48k, so that sets the PLL 1. So S401 set the input format, which I think is LSB justified 16 bits input, but it might be I2S bus input, don't know. Mute is off over here, de-emphasis we don't want to know about. So we are going to use I2S3, and we've got a choice of pins, but we're using PA4 for the word clock, or the word select. We're using PC1 for the data line, and we're using BC10 for the clock. So I've actually, for convenience, compiled all that onto a nice little spreadsheet. So I am going to take that spreadsheet and turn that into wires. Okay, so here she is, all wired up. Hindsight, not terribly sure about those two bus sort of arrangements there. These are just all the option lines that come out this side. Put them on like that because I may well end up changing them. And yeah, we just have 3v3, which is the red and black, and clock, left, right, select, and data. So I am going to now move the camera a bit. Look at the nuclear. Oh god. Get my meter, which is here. And then in beat mode. You can't see it, but you can hear it, and sanity check the connections. Right, V in should be 3v3. That's good. Ground is that one. Good. Those are the important ones, because if they're wrong, probably destroy it. We'll buzz through the others. So B clock is left 1. B clock is that one, and that's left 1. Cool. WS is left 32. WS is W cell it is on this. That one. And that's 38, 36, 34, 32. And data is 36. Data is D in on here. And that's 38. 36. So I reckon we're wired up correctly. So the next step is to generate some code to drive it. Now eventually it'll be connected up to the audio sockets on the mean green box via these soldered connections, but for now I've just plugged it's just a 3.5mm stereo, and that goes to the Pico scope. I only had one of these that I could find, so this sort of lash up connects the other channel. Oops. So if it makes a noise, we'll be able to see it on the scope. Okay, so to drive our I2S interface on the STM32, we are going to use the HAL I2S generic driver, and all the initialization stuff I'm guessing is called set up and called automatically by CubeMX. And here we go, 3 operation modes are available. Polling mode I operation, that is what we are going to use for start offs because it's the simplest, just to see if we can get it running. And then there's an interrupt mode and DMA mode, that is the mode we will want to use eventually. So we want to look and see if we can find this function. Right, IO operation functions, yep. And here it is. And here it is. So we give it a pointer to a type def structure, a data buffer, the size of the data sample to be set, and the timeout duration. Timeout in milliseconds possibly. Oh well, we'll find out. So should we plonk that function in some code? Now I've written MG loop. That's the MG loop that we're using for the display. So this is one, and this code here just generates a triangle wave of about 440 and 660 Hz, just something that's recognizable as to whether it's working or correctly or not. So it'll go around the loop, and when it's done that, it'll cause this function. Now what is HAL status type def? Are we just going to park a value in there for now, I think. So status equals, and we're going to go status. Worst comes to the worst, we can do a break and just examine it. Okay, so it's got to be a handle to an I2S handle type defs. So if we look in main.c there. Oh no, that's me. Oh, there we go. MX I2S3 init. So it's called a function to init it. That's good. Oh, there we go. I2S handle type def. Is that what we are looking for? I2S handle type def it is. So we want then to pass it a pointer to that. and that UDA1334ATS P data we want to pass it pointer to that, and the size will be that. Timeout 100. Not entirely sure what units we're looking at there. So that ridiculously should make a noise. Shall we run it? Okay, so I think I've fixed the compilation problems. Okay, so I like to have lots of projects on the go because it means I don't get bored doing one for weeks and weeks like I did when I was at work. However, it does mean that I forget in between working on something and working on it again how to get it to work properly. So now I've remembered how to get this thing to work, to go to download and run code. So I need to stop it because I've just got an LED flashing. I need to press, well, I'll do it from the menu and you can see what I'm doing, and it should chug away like that and give a load of stuff like that. And there's a little go button here which I can press. It seems to think it's running. So can we look at the scope trace? Nothing. Ah well. So what I shall do is put the scope on the lines that drive the audio chip and see if there's anything happening there. Okay, got scope probes on the left right select and bit clock. So shall we repower it up and see what it does? Disconnected it while I was fiddling around. In we go. Right, shall we see what the scope says? Okay, shall we fire the code up again? Now I need to go debug. And start it running, and let's look at the scope. Oh, okay. So it looks like we've got clock and left right cell. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's 16 clocks per left and 16 clocks per right. So that looks good. Now I am going to put that probe clip on the data line and shall we see what that's doing. Don't breathe or it'll fall off. Yep, that's on the data line, and that looks as though there's sort of data happening. But you can see there are gaps appearing. And is that where it's stopping to calculate more samples? And would the fact that it's breaking up like that upset the audio chip to the point it won't produce any audio? Okay, so I'd use the GPIO pin which drives a little green LED on the Nucleo, so it goes high all the time the transmit function's running and goes low at the end of it. So let us see what the situation is then with that. Okay, yes, and here we see when that GPIO line goes down when we're calculating a new buffer. It doesn't calculate it in time. We can go into more resolution, hopefully, yeah. So you can see we get actually one left and one right to calculate it in, and it's taking maybe half as long again. And I guess possibly the audio interface chip PLL just can't get going and produce a valid audio clock if that's happening every so often. Okay, so I decided to do what I should have done before and check all the connections, and I discovered that the power input, the VIN to the board, that connection was dry jointed and not working, so there was no power to the audio output chip, so not surprisingly it wasn't working. Okay, so I fixed that, and one scope probe is on the, well, it's the LED output I'm just using as a general output pin for checking the timing. The other pin is on the bit clock, the other scope probe should I say is on the bit clock. So shall we see if we can now get it going? Okay, so I've also further simplified the code and got rid of the triangle wave generation, and I've just taken the buffer and filled it full of values which give one channel ramp up, so a sawtooth ramping up, the other channel a sawtooth ramping down, and just keep firing that out over and over. So we set the pin high, we call the function which throws out the buffer. This just allows me to put a breakpoint if it gives an error. We then set the GPIO pin low, and there we go. So shall we try it? Run debug. Yeah, okay, it's happy. So we'll fire it up and go to the scope, and there we go. Yes, because as it blocks, it polls. Most of the time it's away in that function, then it comes down and all it does is go round and call the function again. And happily we can see it's not upsetting the clock timing. So should we see if we have any output from it? That is working. We have audio output. That's what we're expecting. $750 Hz, which is about what we're expecting. Okay, so now shall we see if we can get it to work with the DMA? Okay, so let's see if we can set up our I2S for DMA. So if we look in the CubeMX, we have some DMA settings. Do we want to add a DMA? We do. Select 33 transmit. Right, we've got not many settings here. Increment address. No, the peripheral it doesn't. It always talks to the transmit data register. The memory does transmit. What about data width? I'm assuming, well, byte is obvious, but I'm assuming word is 32 bits, so we want, I guess, half word. Use cipher normal. Should we say circular? Should we give that a try? This is getting into a slight grumble here that the documentation doesn't seem to be particularly good, particularly informative. So we're just guessing here. We're just guessing. So generate code. And it's thinking about it. No, the project is already open in here. So you call the HAL I squared S transmit DMA function to set it going, I think. And then you've got two callback functions, a half callback and a full callback. Which means once you've had the half callback, you can write to the bottom half of the buffer, and the full half callback you can write to the top half of the buffer. And an error callback, which will stick a breakpoint in case there's an error. So the half callback I've set the GPI pin high, and the full callback I've set it low. And I was going to go around and call this every time, but I'm not sure we do. So those are commented. Okay, we have a quick look at the datasheet. So there we have the two callbacks. Two transmit callbacks and a transmit DMA, and it says transmit an amount of data in non-blocking mode with DMA. Well, that's not very informative. And it says the I squared S is kept enabled at the end of transaction to avoid the clock, so it keeps running. So that's where I thought that maybe if you kept if you use circular DMA, it would keep outputting forever. And so yes, you've got pause and resume functions if you need them. We don't. We're going to set it going and go TX half completed callbacks, and it's not telling us anything useful. So we shall just press on and get it running. So I will, in this instance, build all, because I'm not sure it'll build. Okay, it seemed to be happy. So shall we upload it and see what it does? Right, it's uploaded it, it's at the start, so we'll run it and see what we get on the scope. The answer is not a lot. No, on the full callback we want to reset that so it'll come around here and call the I squared S transmit again. Okay, so is that doing anything? Go back into the scope. No. So I have set the DMA mode back to normal rather than circular, and done a generate code off camera. And here I have set it so the half complete callback sets the pin, and the full complete callback clears the pin and sets DMA TX to 0. So when it gets to here, the next time it comes around the loop, it'll do a DMA transmit again. And while I think of it, I will put a breakpoint in there, so if that function does fail, we'll know about it. So just stop it and hit debug. Wait for all this stuff to chunter on. Right, so we start it, and well, it's doing something. That is supposed to be the clock. Obviously nothing happening, and you would have thought it would have gone up and down at equal intervals. This is, you know, putting out half the buffer each time. And if we look for the second half of the buffer, it's taking 10, well no, 13 or 14 microseconds to put the data out, and it should be putting 32 samples out at 48 kilohertz, so it should be taking whatever that is, 2/3 of a millisecond. So it looks like it's just the DMA is just throwing the data into the I2S transmit register as fast as it can, with no heed to how fast the I2S is outputting it. So there is something seriously wrong. So I've done a bit of digging on the internet, and I'm not the only person who's had this problem of not getting the DMA working with the I2S, and the general vibe on the forums and just posts is that the CubeMX and the HAL are clunky and buggy, and what you should really do is, like a proper embedded program, is get down in amongst it and write to the registers. For the last however many years of my working life, I worked pretty much exclusively on microchip PICs, and this is what I did. And yes, you know what you're getting, but I found you can spend ages and ages chasing one bit I've got wrong in a register somewhere, and end up spending longer just trying to get peripherals doing what I want them to do than actually writing the code of the application I'm trying to create. That's why I thought, oh, the CubeMX and the HAL just make all that easy, and it just does all that for us, and we can concentrate on writing synthesizer code. So the question is, should I abandon the CubeMX and the HAL and just start a new project and write to all the registers from scratch? I just feel, because I don't know the STM32 that well, this is going to take me a long time, and I really just want to get on to writing the synthesizer stuff and not learning the STM32. And okay, I might end up having to do that, but for now I am going to take advantage of the fact that the HAL is not a black box library. It is actually supplied as source code, which compiles with your application code, so I can fish out those routines, those functions like the I2S, HAL I2S transmit function we called, and look at what's in them and find out how it works, and if necessary create my own function that just takes the important bits out, and also go through the initialization code and compare it to what the datasheet thinks ought to happen, and see if I can find out where it's going wrong. So that's what I propose to do for now, and probably do most of it off camera, because I guess nobody wants to watch me going at data sheets. And hopefully we'll be able to move on. But in the meantime, we did actually get it running on the scope, so shall we see if we can plug it into the audio amplifier and at least we can see how noisy it is. So we've got this wire connected to those connectors round here, round the back of the computer, up to there. Sorry about the moving camera. Okay, I've put the code back I've taken the DMA off so we know it produces an output. I've recompiled it and enough of that, but as you can hear, no nasty digital noise, so it's looking good. And that's all powered off a USB hub, so normally you expect it to be noisy as anything. Okay, I've commented out my array definition of numbers, so now all zeros, so it should produce silence, but it will actually be up and running. Small click as it starts, but I can't hear any noise. Okay, it's hard to tell low levels of noise because the fan's going on the laptop and what have you, but I did it on headphones, and with it loud enough to sort of almost take my head off, I could just hear a little bit of hiss coming out of that audio interface. So I am well pleased with that. That is going to do our job. So on that more positive note, I shall sign off for this video. Subscribe, comment, thumbs up, and for now it's goodbye from Triplicate, home of interesting and sometimes frustrating electronics. Goodbye.